Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer questions from sample paper number 5, the 4th edition of RK Bali navigation book. Very useful and very important for your exams. Let's start. Quadrantal errors associated with aircraft ADF equipment are caused by misalignment of the loop aerial, skywave, ground wave contamination, signal bending by aircraft metallic surfaces. So correct answer is option Charlie. So let's consider this is your aircraft. Now this is your north datum. These are the wings. Now this will be the longitudinal axis of your aircraft, and this will be the lateral axis of your aircraft. Now if there is any radio signal originating from NDB station along this longitudinal axis, along this direction, east, west or north and south, there won't be any bending of signals. There won't be any bending of signals. So if any signal is coming from either of these four directions, it will not suffer from a quadrantal error. But if a signal is coming from any other direction, it will definitely suffer from quadrantal error. Let's say there is a signal which is coming from 045 degree. Now the electrical conductivity of this aircraft will bend this signal in such a manner that it gets aligned, more or less aligned with the longitudinal axis of aircraft or the lateral axis of aircraft. So for example, if it's coming from 045 degree, the electrical conductivity will bend such that it gets aligned with the longitudinal axis of aircraft. So the real direction is 045 degree, but the apparent direction has become less than 045 degree. So something like 020, 030, any direction less than 045. So again, this is a false information. If any radio signal is coming from southeast direction, like 130 degrees, something like that. So again, the electrical conductivity of aircraft will bend this signal such that it becomes aligned with the longitudinal axis of aircraft. So the pilot will get an erroneous information. This signal is coming from a direction more than 130 degrees, 140, 150 like that. Now if a signal is coming from southwest direction like this, 225 degree, 230 degree, the electrical conductivity of this aircraft will bend it around to align it with the longitudinal axis of aircraft. So the signal will appear to be coming from a direction less than 220 degree, 225 degree, let's say 210 degree, right? So if the signal is coming from the northwest direction of aircraft, again the electrical conductivity will bend it around and the signal will appear to be coming from a direction which is more than northwest, 350, 340, something like that. Okay, so this is your quadrantal error, which happens mostly in the quadrant, southeast, southwest, northeast, northwest, like that. A VOR and DME are co-located. You want to identify the DME by listening to the call sign. Having heard the same call sign 4 times in 30 seconds, VOR and DME call signs were the same and broadcast with the same pitch? No. DME call sign is the one with the higher pitch that was broadcast only once? Yes. DME call sign wasn't transmitted. The distance information is a sufficient proof of correct operation. Wrong. So 4 times. So the first three times you will get to hear VOR ident, and the last time and the fourth time you will get to hear DME identification. And the DME identification is one with higher pitch. Okay, so that's how you differentiate between them. Next. So you are going to remember this. Both transmit the same call sign. 3 or 4 idents every 30-second period. The VOR transmits 3 out of the 4 and DME transmits the last fourth one in the last 10 seconds. So total 40 seconds. First 30 seconds VOR 3 times. The last 10 seconds, the 40th second, you will hear the fourth DME ident. Next, question 83. When 95 when 95 nautical miles When 95 nautical miles from a VOR, you commence a descent from flight level 330 and you want to arrive at VOR flight level 100. What rate of descent you need? So let's say this is your VOR station. This is your aircraft here. This is your descent path. Okay. You are at flight level 330, that is 33,000 feet, and you want to come down to 10,000 feet. Distance 25. Okay. So speed, your speed is equal to 250 knots. Okay. So distance is 95. Speed is 250. So time will be equal to distance divided by speed, 95 divided by 250. So 95 divided by 250 is equal to 22 minutes. 0 hour 22 minutes. So you have 22 minutes to descend. So what will be your rate of descent? Rate of descent is nothing but change in height, change in height divided by time. So you are going to descend 33,000 minus 10,000, 22,000 in 22 minutes. So 22,000 divided by 22 is 1,000 feet per minute. So the correct answer here will be 10,591, 10,100, 1,150. So 1,000. So correct answer is option Charlie, the closest option. Okay, 1,000 feet per minute. Radio waves are coming from the land to sea surface. The radio waves are coming from land to sea surface. The waves will bend away from the normal. So this is another NDB error called coastal refraction. So let's say this is the sea surface. This is the land surface. This is your NDB station here. Now whenever this NDB transmits a radio signal that travels from the land to the sea, the moment it reaches the coastline, it will refract away from the normal. Okay, so this is called coastal refraction error. Next, what will be the rate of descent when flying down a 12% glide slope at a speed of 375 knots? So formula is tan theta into 100 equals to slope in terms of percentage. So 12% 100 into tan theta. Tan theta will be equal to 12 by 100, 0.12. So tan inverse 0.12. So tan inverse 0.12 shift tan inverse 0.12 is 6.8 degree or approximately 7 degree. So now rate of descent equals to speed divided by slope, corrections, multiplied by slope upon 60. So speed is 375. Knots multiplied by 101.3 feet per minute multiplied by 7 degree divided by 60. So rate of descent will be 375 into 101.3 into 7 divided by 60, 4432 feet per minute. So 4430 approximately. Okay. So let's check 85, 4430. So the closest answer here is 85A. 85A. Okay. Next. At 80 nautical miles from a VOR, aircraft commences descent from flight level 330 in order to arrive overhead VOR at flight level 100. What rate of descent is required if the mean ground speed is to be 240 knots? So what will you say? VOR is here. Aircraft is 80 miles away. Flight level 330, that is 33,000 feet. VOR 10,000. Speed is 240. So time, distance upon speed. So distance 80 divided by 240 will be equal to 20 minutes. Now rate of descent equals to change in height divided by time. So 33,000 minus 10,000 is 23,000. Time is 20 minutes. So 23,000 divided by 20 minutes is 1,150 feet per minute. Okay. Aircraft is on a ILS 3-degree glide slope which passes over the runway threshold at a height of 50 feet. The DME is 15 miles. What is the height above the runway threshold elevation? Above the threshold elevation. Now, this is a tricky sum. Let's say this is your runway and this is the threshold of your runway. Now, the glide slope that you are following is 50 feet above the threshold. Is 50 feet above the threshold. Your aircraft is over here. Okay. DME is 15 miles. Okay. Glide slope is 3 degree. So let's apply First, we will find aircraft vertical distance, x. So let's use tan theta. Tan 3 degree equals to opposite upon horizontal. So 15 multiplied by 15 nautical miles multiplied by tan 3, 15 tan 3 multiplied by 15 is 0.786 nautical miles. Convert that into feet multiplied by 6,000. So you will get 4,716.7. X equals to x is equal to 4,717 feet per minute. Okay, so that means your aircraft is 4,717 feet high. Okay, and now you have to find out the height of this aircraft above the runway threshold. So above the threshold, that means from here. So you are going to add this 50. So the final height will be aircraft is 4,717 plus 50, that is equal to 4,767 feet above the threshold. Okay, so you will select the closest option. So 87 is Charlie. Yeah, so you will select 4550. That is the closest to 4,700. Okay, now they must have used track error formula 1 in 60 rule. If you use that formula, you will get some different value. So the approximate answer is this. Next, in a chart, if meridians and parallels of latitude cut each other at 90 degrees and the scale is correct, the chart is said to be orthomorphic. So there are two properties of an orthomorphic projection. Meridians of longitude and parallels of latitude must intersect at 90 degrees and the scale must be correct. Next, 89. For an aircraft at a height of 1,500 feet, 3-degree glide path will occur at what distance, right? So, you aircraft is at 1,500 feet, 3 degrees away. You have to find x. So again, use tan formula. Tan 3 degree opposite. Opposite is 1,500 feet divided by distance. So x equals to 1,500 divided by tan 3. So that is equal to 28,622 feet. In nautical mile divided by 6,000. So it is equal to 4.77 nautical mile, approximately 5. So option Bravo. Conversion angle increases with increase of latitude and decrease of d long, decrease of latitude and decrease of d long, increase of latitude and increase of d long. So convergency angle is the angle between your great circle and drum line, right? And as latitude increases, convergency increases. So it will increase with increase in latitude, and as the difference between two longitudes increases, again the convergency will increase. So convergency angle is nothing but half of convergency, right? What is convergency? Convergency is again nothing but d long in degrees multiplied by sine lat. So it's proportional to latitude and also proportional to d log. So Charlie is the right answer. So this concludes our lecture. I hope you have understood all the 10 questions I have answered and explained in this lecture. Practice these questions many times, become confident and set a time also so that you may become time efficient as well. All the best. Share this channel with your friends. Subscribe if you haven't yet and press the like button if you have liked this video lecture. In my next video, I will solve the next 10 questions. So don't miss that.